Saturn's largest moon, Titan, is a dynamic ocean world, entirely obscured by a dense nitrogen and methane atmosphere. This diagram compares Earth's baseline metrics directly to Titan's surface. Down on the ground, the atmospheric pressure is 1.5 bar, the gravity is low, and the temperature is permanently locked at 94 Kelvin, or minus 179 degrees Celsius. At these temperatures, ultraviolet radiation breaks down high-altitude methane, forcing it to recombine into complex, heavy organic compounds called tholins. These organics rain down, creating a frozen snapshot of chemical pathways that precede biological life. To study these prebiotic materials in place, NASA is sending the Dragonfly mission, an autonomous rotorcraft designed to land on Titan, collect samples, and analyze them using onboard spectrometers. To conduct that chemistry, engineers face an immediate hurdle. They must build a mobile laboratory capable of permanent immersion in a dense, flowing cryogenic fluid without its internal components freezing. The vehicle built for this environment is an 8-rotor, nuclear-powered drone designed to fly tens of kilometers across Titan's organic dunes. Its primary hazard is the atmosphere itself. Titan's high-pressure, low-temperature air is highly convective, acting as an absolute heat sink that relentlessly drains thermal energy away from the lander's interior. Yet, despite operating in a deep freeze, Dragonfly also runs the risk of overheating. When the rotors spin up for high-power flight maneuvers, internal components generate intense, rapid heat spikes. Dragonfly employs a tightly controlled thermodynamic architecture that harvests heat, traps it inside, and selectively vents it to maintain internal equilibrium. Mastering this balance is the prerequisite for the entire mission. Without it, the instruments cannot survive long enough to meet any of the astrobiology goals. The heart of that survival strategy is the multi-mission radioisotope thermoelectric generator, or MMRTG. While the MMRTG charges the main battery, its true value for survival is thermal. The decaying plutonium inside provides approximately 1,670 watts of continuous, vital waste heat. This schematic maps energy distribution. On the right, a fluid loop connects to the red MMRTG heat exchanger. Following the dotted lines, metal tubing runs the lander's length, circulating refrigerant to pull thermal energy inward to the electronics and battery. By utilizing this loop, the MMRTG acts as a forced central heating system, ensuring core components stay operational in the cold. Generating heat is only the first step. The vehicle must then trap that energy to counteract the intense convective drain of the atmosphere. To achieve this, the interior components are wrapped in a 5-centimeter thick layer of closed-cell rigid Rohacell 31HF foam. This specific material maintains an extremely low thermal conductivity, less than 0.035 watts per meter Kelvin, while remaining highly transparent to radio frequencies, allowing internal antennas to transmit data. Because the lander requires physical penetrations for motor arms and camera windows, engineers use a thermal exterior losses budget to track every leak. Each necessary structural mount pierces the foam, creating a pathway for precious heat to bleed out into the Titan environment. Accounting for every one of these leaks is what prevents the delicate mass spectrometers from freezing solid before they can analyze a single organic molecule. Once the interior is insulated against the cold, Dragonfly faces the opposite challenge, surviving 30-minute powered flight sessions. This thermal model shows an active excursion. The hotkeys diagram highlights severe internal temperature spikes from rapid battery discharge that could exceed safe operating limits. To absorb this energy, the system relies on the battery's high thermal capacitance to buffer against rapid thermal shocks. To augment that capacitance, aluminum fin extrusions sit between the battery cell stacks. Small tube axial fans engage during flight, actively blowing heat off the fins and rejecting it into the lander's internal atmosphere. By utilizing its own trapped interior air as a temporary heat sink, Dragonfly safely diffuses the thermal load of its flight maneuvers. To maintain equilibrium, the lander requires precise Vernier-style temperature adjustments via thermal trim devices. These are foam-capped mechanical louvers that open via linear actuators, directly exposing a section of the uninsulated interior wall to the freezing Titan atmosphere. By placing one trim device at the fluid input of the MMRTG and another at its output near the battery, The vehicle can precisely regulate the temperatures of both its heat source and its power storage. Outside of this internal shell, other components face the environment head-on. The mobility motors that drive the 8 rotors sit entirely exposed at the ends of the structural arms, subjected to the constant 94 Kelvin chill. Rather than wasting continuous power on survival heaters, these motors are allowed to freeze. Before flight, a targeted 90-watt preheater warms the bearings for 5 minutes to reach minus 65 degrees Celsius, after which the motors stay operational using their own internal resistance heat. Survival on Titan is a mechanical juggling act of continuously trapping, distributing, and venting energy to maintain a habitable interior. This final exterior thermal model maps the culmination of that system. Labeled Cold Survival, it shows the exact temperature gradients across the hull and rotors, verifying that the insulated interior remains viable while the exterior reaches equilibrium with the cold. Engineers can trust this architecture because Titan provides a distinct advantage. Its environment is incredibly stable. There are virtually no temperature swings between day and night or across the seasons. Because the external variables are known and constant, the entire thermal control system can be rigorously validated on Earth. Engineers place a full-scale lander inside high-pressure cryogenic chambers to verify the exact flow of every watt of energy. Maintaining this thermodynamic stability is the only way to deploy drills and mass spectrometers onto the Shangri-La sand dunes. By mastering the thermal mechanics of a frozen world, Dragonfly will finally allow human chemists to decode the alien organics raining down on Saturn's largest moon.